This presentation is for IEEE DML application. I'm honored to present millimeter wave and terahertz integrated circuit and system for 5G or 6G wireless and sensing. My name is Kaixue MA from Tianjin University. The work is supported by Tianjin Key Laboratory of Imaging and Sensing Microelectronics Technology. Here's the outline of my presentation. Firstly, I will introduce the background of this work, and then introduce MM wave IC and systems, which includes the multi-tank model and application in VCU, etc. And then we'll introduce some example of ×2 and ×3 frequency multiplier, and is used in a 5G LO. And we'll also introduce a 5G millimeter wave multi-band multi-standard transceiver, as well as the beamforming chipset and its antenna in packaging. And finally, I will introduce the CISO-based MM circuits and systems. In the third portion, silicon-based terahertz circuit and system, I will introduce the 140 GHz 4x4 FMCW radar transceiver SoC and its also antenna in packaging. And then we'll introduce a 220 GHz 4x4 16-element imaging transceiver SoC and also antenna in chips. Finally, I will give an introduction of 2.5 terahertz and 28.3 terahertz imaging SoC and demonstration system. Finally, I will give a conclusion of my talk. 2020 is the first year for 5G adoptions. The frequency band used is mainly sub-60 GHz, and which have very good coverage. With progress of 5G, millimeter wave like 28 and 39 GHz is every issued worldwide to support the future B5G adoptions. And recently, the 6G white paper is released. And for B5G and 6G is going to have a wireless communication and sensing network to link the satellites and the ground and even the sea. For all these applications, millimeter wave and terahertz is actually a very good candidate to support these applications. MM wave and terahertz have much wide absolute bandwidth, but they have more path loss due to a small wavelength. And it also needs a beamforming to have better ERRTG for better coverage. And for millimeter wave and terahertz, it actually tend to have both wireless communication and sensor applications. All of these applications actually need a much more RF millimeter wave circuit system. And based on investigation and low cost, front end are key for future 5G and 6G success. Commercial silicon-based IC is dominant in the IC market, about 90% of the total market share, due to the low cost for mass production of the silicon process. And is widely used in the analog, digital, sensor, and RF millimeter wave for PC, phone, and also automobile. As compared to the traditional gallium arsenide or InP process, the silicon process like CMOS, BiCMOS, or SOI CMOS have the advantage of the multiple mental layers, which is very good for high integration level, and it also have a very low cost, especially for mass productions. And of course, it has silicon process have these advantages of high substrate loss, and the resistivity of the substrate is only 10 ohm per square, which is much low as compared to the macro board like Rogers 10/7. Here we give an example. The P substrate contributes to the loss up to 8 dB for second order 60 GHz bandpass filter or 77 GHz bandpass filters. And to cope with the loss issue, we propose multi-tank circuit model to significantly reduce the substrate loss of a silicon process. Here we give the multi-tank model as shown in the figure, and we derive the matrix based on the Kirchhoff current law. We derive the matrix to get two operant frequency omega-1 and omega-2 in the equation. Based on equation, we can clearly see the operant frequency and the Pauli factor is clearly related to the tank number. That means the increased tank number will reduce the frequency and also enhance the Pauli factor of the equivalent resonators. So by using multiple mental layer of silicon process, we can build each tank on 8 different mental layers. And through this different mental layer to use a magnetic coupling to enhance the polyfactor of the equivalent resonators. And by doing so, we can also lower down the operation frequency by increased tank number, which contribute to the size reductions. Actually, we filed the US patent in 2010, and the patent is cited by a multinational company. Now this kind of method is widely used in the publication as well as in the commercial products. And here we show an example. We use a multiple tank to build the 5G reconfigurable ×2 and ×3 multipliers. The background is that the frequency multiplier is high demand for LO operations. We propose a reconfigurable both support ×2 and ×3 ILFM. We propose the first dual feedback loop architectures. That means we have a dual core in ILFM as a schematic shown in these figures. And the 3 transistor can support core selection to support wide tuning range of the ILFM. And the negative transconductor of the transistor GM to enhance the polyfactor of the tank. By doing so, we can achieve low phase noise and as well as low power. Here we summarize the performance of our proposed design. The frequency actually can cover 20.7 to 40.3 GHz, about 71.6%. And the DC power consumption is actually 12 milliwatts or 9.6 milliwatts for double mode or triple mode. We have very good harmonic rejection ratio. And the core chip area is only 0.07 millimeter square, as the photograph shown in the figure 3. And we also propose a CISO-based millimeter wave circuit system. Here we give an example. We use the CISO to design the K-band low-noise amplifier for satellite LNB applications. As the background, we know for satellite applications, for better link budget or coverage, is actually need a very low noise figure, low noise amplifier. And for the traditional LNB, is actually need a mental case for packaging and need high-cost microwave substrates. Here we propose CISO-based LNB design. We use a pattern substrate for loss reduction, and the whole circuit we just use a FR4 material for both packaging and also for the circuit design. That means we can achieve low cost and also the lightweight. And then we summarize the performance. The low-cost purely FR4 material used, the circuit itself is actually self-packaging architectures. And inside we actually use a substrate hollow to further reduce the loss. By doing so, we achieve a very low noise figure LNA as compared to the state of the art. We achieve 0.8 dB noise figure, which much lower as compared to the others. And then we also build a terahertz image area for sensor applications. Here's a 220 GHz chipset. First of all, you do some building block of 220 GHz from the terahertz doublers, and we propose distributed balloon together with the dual tanks. The most transistor capacitor neutralization is, and also bank transformer-based balloon and a dual tank to further reduce the matching loss. By doing so, we achieve 208 to 233 bronchial doubler with a 1.1% power adding efficiency doublers. By using this kind of building block like the bronchial doubler and the bronchial converters, we built the imaging area system as shown in figure 4, the topologies. And in figure 5, this photograph is our build the systems. And in this one, we actually use a 16 element antenna-in-chip. We have the performance as summary in these tables. We can support detect range of less than 0.3 meters and range resolution of 1 centimeter. The key feature for this area SoC is a single chip can support both transmitter mode or receiver mode, and also share the common antenna-in-chip area. And we have a common LO to support even larger area. And then we also build the 2.5 terahertz imaging system and also the SoC. Here we show the block diagram of a 2.5 terahertz imaging system. Here's the setup for this experimental. And we take a photograph of an envelope to see what's the object inside. Based on photograph shown in the figure 5, we can clearly see the parts inside of the envelope is actually the screw and the blade. And beside the 2.5 terahertz system, we also build a silicon-based 28.3 terahertz area, support 128 and 128 elements, SoC and also thermal imaging system. Here I give a conclusion of my talk. New methodologies of multi-tank model is proposed to elevate the substrate load of a commercial silicon substrate. And the multi-tank model is used in VCU, long-term simplify, and switch, etc., to verify the advantages of our proposed method. And our proposed seesaw-based medium wave circuit and system are also introduced. And finally, I will present the 5G or 6G multi-standard mid-wave and terahertz image sensing IC and also SoC are also introduced. That's my all talk.